Hi guys. Last week I uploaded a checkpoint, a practice checkpoint sort of thing, which had a range of problems involving different types of functions that we've been studying. But in particular, in question 6, there was a really tricky problem in there that I thought might be worth going through. And the point of question 6 wasn't necessarily that you'd all be able to get it out on your own. It was that you'd sort of work through the process and actually spend a bit of time struggling with it and thinking about different things that may or may not work. So sorry about that. But I thought I will go through how question 6 works. If all you want is the answer, then skip to the end of the video because I'm going to go through a few things that don't work first, and then I'm going to show you how you would approach a problem like this. And this is actually probably a bit of a new technique that we haven't looked at before. It's going to be a graphical technique, but it's a little bit clever. Okay, so what we're going to do is we're going to look at this problem here, and when you're asked for intersections, and number of intersections in particular, you might be thinking, oh, what I'm going to do is I'm going to set these equal to each other, I'm going to try and solve, and maybe there'll be a discriminant problem somewhere in there that'll tell me whether there's 0, 1, or 2 solutions. Now, 3, we've never had to deal with that before, but maybe I think your first instinct, it's a pretty good instinct, is to set these two things equal to each other and see if we can solve for x. So that's the first thing we're going to do, and I just want to show you that to see maybe what the problem with doing that is. So let's set these two things equal to each other. Already this is not looking promising because we don't really know how to deal with those. But you might think, if you're being really clever, you might think, well, the biggest problem here is that we have a fraction with an x squared on the bottom. So let's multiply everything through by x squared. So I'm going to multiply this by x squared and I'm going to get 1. I'm going to multiply this by x squared and I'm going to get 2x cubed. Multiply this by x squared and I get kx squared. And okay, starting to look a little bit better. How do we approach a cubic? Okay, we put everything over to a single side. Potentially you might be able to guess a solution and then use factorization, polynomial division, stuff like that to solve. But remember, when we go to cubic, we kind of have to guess one of those solutions before we can do anything else. Now, there is a cubic formula, but I promise you it is horrendous and you don't want to deal with it. You might want to just plug that into your CAS. So you might stick that into your CAS and get solve 0 equals 2x cubed plus kx squared minus 1, and solve for x, and you would get, this is the point where I would normally pause my video and do this on CAS, but my CAS software is still not working. So I'm actually going to use Wolfram Alpha instead, which is just an online sort of basically a CAS, a little bit smarter than a CAS. So I'm just telling it, solve this equation for me, and solve it for x, please. I hit enter, and it thinks about it for a little while because it's not easy, and we get something genuinely horrendous. Now, you might be able to peer through this horrendous thing and see in it certain values of k that are going to give you 3 solutions. And let me give you a sense of how you would do that. Well, you want all of your square roots, any square roots that you're taking, to not be negative. So you might look at this and say, okay, 27 minus k cubed. Ooh, I better have a k less than 3, maybe. Oh God, I don't know. You'd be doing a lot of that, basically. Now, honestly, that's a really tough idea, and when it comes up on your CAS, it's even uglier. And I promise you, there's a simpler way of approaching this that doesn't involve horrendous expressions that have cube roots of square roots multiplied by other square roots in them. Okay, so you could do this, and you get horrendous maths. And maybe you can look at that horrendous maths and you can see for what values of k you get 3 nice solutions and for what values of k you don't. But to be honest, I looked at that and I gave up. So your next instinct, if you have good mathematical instincts, is instead of solving algebraically, maybe we should just plot them. And maybe we should just have a look at what it looks like when we plot them. So we're going to go to Desmos, and we're going to plot the two of them. And you'd be doing this on your CAS, obviously, probably. So you're on your CAS screen, and you can actually insert a slider on the newer CASs. So if you just put in a plus K or something in your, when you put in a function, it'll actually ask you, would you like to insert a slider? Now the sliders are very hard to operate on that tiny little screen, but they're much easier to operate on Desmos here. And what we were looking for is, well, we can see at the moment there's only one intersection, but we can see pretty easily that if we change the value of K, there's going to come a time when we have three intersections. So we got this one here, and this one here, and this one here. And okay, we've got three intersections, and you can play with that K value until you find the K value where you first start getting two intersections. And that's a pretty good way to do it. You could definitely do that, and we could find that it looks like K is going to be somewhere around 3. And you might be happy with that, and you might say, okay, well, K is going to be bigger than 3, or 3.1, or 2.9, or something, somewhere around there. But you're not going to be sure that you've got the exact right value of K. So using sliders, we see that K needs to be around about 3 to get just 2 solutions, and then any bigger than that, and it seems to give us 3 solutions. But yeah, it's a bit of an approximate method, and you'd probably get some marks for it, but you wouldn't necessarily get full marks for this. So the last thing we're going to do is we're actually going to do something related to this, or sort of a little bit related to this and a little bit related to this. We're going to plot something, but it's not going to just be those two graphs separately. What we're going to plot is the difference between them, because where they intersect is where the difference is 0. So we're actually going to look at this line here, basically. Well, let me just put it in here. So we're saying 1 over x squared equals 2x plus k. I'm sorry about that sunlight on my screen. And we're going to just move them both to one side. So we're going to plot something like 1 over x squared minus 2x minus k equals 0. Okay. So you can't plot something that only has an x in it, not a y. So what I'm going to do is I'm not going to plot this equation. I'm going to plot this equation. Okay. So what I'm plotting is just the left-hand side of this, and then I'm going to look at when does this equal 0. So here we go. So what I've got is I've plotted, if we can see up here, 1 over x squared minus 2x minus k, and you can see that it's only got one x-intercept at the moment, and k is set to 0 at the moment. But we can change the value of k, and as we change the value of k, you can see that for certain values of k, we get 3 x-intercepts. And those 3 solutions correspond to 3 solutions to this equation, but that is just this equation here lurking in disguise. So the x-intercepts of this are the solutions to this, which are the solutions to this. So the x-intercepts of this graph, this purple graph here, are the intersection points, the x values for those intersection points. And we can see there's 3 when k is 3.8, but when k is, 0.5, there's only 1. So similarly to before, we could vary k, and we could see that, once again, it's somewhere around 3, but we still don't know if it's exactly 3, frustratingly. Okay, so here's what we're going to do. Yeah, so I've called this function here f of x, so that's f of x there. What I'm going to do is I'm actually going to plot a related function, g of x equals to 1 on x squared minus 2x, and I'm just not going to put the k on there. So let's just do that now. So let's plot that function there. So we've got f of x here in purple, and in the blue line here is just the same function, but I haven't put the minus k on. So what that means is what's happening is K is a vertical translation from the blue function to the purple one. So the purple one is our actual function, but we want to know whether it has 1, 2, or 3 x-intercepts. But what is K actually doing? Well, it's just a vertical translation. And we can see that if we plug in a certain x value here. On the blue graph, we get 5.16. On the purple graph, we get 3.16. What's K? It's 2. So what's K doing? It's just minusing 2 off whatever values we have. If we make K equal to 1, there we go, then there's just 1 between these. And you might think that's only happening at this point here. Surely it's not happening over here. But we can change the x value that we're plugging in, and we can see that these two really are always exactly 1 apart from each other vertically, because that's the role that K is playing. As a parameter here, it's literally just a straight minus of everything. It's a vertical translation. Okay, well, what that tells us then is that if K is just a vertical translation, then all we're doing is we're moving this blue graph here downwards until it has 3 x-intercepts. But how far do we have to move it downwards? Well, that becomes a much easier question, because how far are we going to move it downwards? We're just going to have to move it as far as this minimum turning point here. We have to get this turning point below the x-axis. If we get this turning point below the x-axis, there's going to be 2 x-intercepts associated with it, in addition to this third one over here. So, by graphing this function without the k in it, we can find this minimum point, and then we can say all we would have to do is drop that down by more than 3, and we'd have the solutions that we're after. So what this tells us is that since there is this thing here has a minimum, so we're going to find that turning point, and your CAS is terrible at sliders, but it's great at finding minimas and maxima. So you can tell your CAS, hey, go and find the minimum on this function, the one that doesn't have a k in it, and it's going to tell you that it's -1, 3. All right. What's the difference between G and F? Oh, it's just that -k. So if k is greater than 3, the turning point is below the x-axis, therefore 3 x-intercepts. And that's actually a general skill that you probably want to add to your little toolbox now, is that if you are being asked to graph something that has some ugly parameter in it, try graphing it without the ugly parameter and see what it looks like, and then think, what sort of transformation is that parameter causing on my graph? If it's causing a nice clean translation, then it might very well be that any turning points and things just move around in a really nice way. Okay, thanks guys. So that's how you would approach that question. Really tough problem. If you made some progress on that, then very well done. And if you managed to do it this way, then very, very well done. You made your own life quite hard. Okay, bye.